not Turing recognizable. Now why is that? So a couple of lines of proof, which I had to jam into, finish it into the board. Now look, we know that ATM is Turing recognizable. And it was, we did that earlier as a proof. Now, if the complement of ATM is Turing recognizable, right? If it's Turing recognizable, and we know that ATM is Turing recognizable, so if the complement is also Turing recognizable, well, if they're both Turing recognizable, then ATM itself is decidable, right? That's what, you know, theorem 4.22 is all about. So if they're both, if ATM is Turing recognizable and the complement of ATM is Turing recognizable, if both of them are Turing recognizable, then the language A suffix TM is decidable. But we know that A suffix TM is not decidable, and we spent 3 sessions proving that, right? With all the weird Turing machine D and all the logical contradictions, and, right? Yeah. D accepts angular bracket D if D does not accept angular bracket D. D does not accept angular bracket D if D accepts angular bracket D. You know, all that kind of ridiculous, you know, contradiction. So we proved that A suffix TM is not decidable, right? But we know that ATM is recognizable, Turing recognizable. Ta-da! You see what's coming? Can you see it? Is it obvious? Right. Okay. So ATM is Turing recognizable. Right? We did that earlier. So if the complement of ATM is Turing recognizable, well then ATM is decidable. But we know it's not decidable. Okay, from theorem 4.11. It says ATM is not decidable. And therefore, the complement of ATM cannot be Turing recognizable. So A of TM is not Turing recognizable. Now that may sound a bit dry and abstract and so forth, but let it sink in, let it penetrate the enormous significance of what it implies. It's just humongous, right? It means that here's a language. Now, Sipser translates tasks into languages. So just, you can translate this into the traditional way of formulating the halting problem I was talking about in the first session. So, you know, this problem is, it's not even Turing recognizable. So there's not even an algorithm that can even recognize the members of this language. Can't even recognize them. So it's even more impotent than the Turing machines that can't decide. I mean, a Turing machine that decides is more powerful than a recognizer. But there are languages, you know, tasks, that for which no Turing machine exists, that can even recognize the strings of that language. In other words, the solutions to the tasks. So there's just, you know, you just give up. There's just no way to find an algorithm that can solve your problem. You know, that can recognize all solutions. There may be some candidate solution pop up, but there's no Turing machine that can test it. It's just, well, it's not just undecidable, it's worse than that. It's Turing unrecognizable. Now, because, well, particularly in the formalism used by Turing with the UTM, the Universal Turing Machine, that was so visualizable and intuitive, which surprises me that Sipser chose not to. He barely mentions the UTM, as I was saying a bit earlier. Just a line or two in passing. Whereas it's sort of a feature in most books on textbooks on the theory of computation. And I'll do another course at pretty much the same level, probably a bit later, with Marvin Minsky's book on finite and infinite machines, as I mentioned earlier, and he has a whole chapter on that. Anyway, bottom line, punchline is that effectively, if you interpret this, this in the form of language, but if you extract out the meaning, there are languages that are not even Turing recognizable. So that implies certain tasks just don't have any solution. There's just no algorithm, no Turing machine, no algorithm that can even recognize whether a particular candidate solution is a solution. Can't be decided. Wrong word. Oh, I'll just leave it. Can't even be recognized. So just total impotence. And it wasn't the first, but it was almost the first. It was came pretty closely after Church found the very first example, as far as I know. But it was certainly most famous, and after that, people really had to absorb the deep philosophical lesson that some things, there's just no solution to some things. Things will just remain forever. You just don't know, right, in effect. And that has intimate links with logic and set theory, and I'll do courses on these as well. Because Turing was, he was pretty much a mathematician. As I was saying in earlier lectures, the whole notion of a general purpose programmable computer is a kind of side effect, a spin-off of his investigations into the foundations of mathematics. He was trying to answer, what's his name? The German mathematician. He's pretty well a top mathematician of his day. Well, it'll come to me. Old age, I think. Or maybe the flu. So-and-so's problems, 23 of them. Which that should help. You're probably screaming at me the name I'm trying to think of. It's just not coming to me. So since then, the halting problem of Turing has become the sort of symbol of this idea that people have had to absorb, that there are some problems that just don't have solutions. Right? And now it's the whole industry, undecidability and that kind of thing, computability. And there are problems that are not abstruse. They're quite simple, practical problems that people want the answers to, that also have there are no solutions for them. So the halting problem symbolizes all that tremendous effort that there's an army of researchers now, one after the other, showing certain types of problems just cannot be solved, just unsolvable. And that's one of the major philosophical lessons to come out of the 20th century. Some problems cannot be solved, and you can prove that they cannot be solved. That's sobering. Right? So we've found an example here of a language that is not even Turing recognizable. So that's worth a trumpet roll. Now, so that's the end of this this board and this chapter. At least the theory part will be followed at some stage by the problem-solving session, which I'll do. I have a backlog, quite a backlog. I think I'll finish the theory before I get onto problem-solving. It's a whole different way of thinking. So I'll finish off by saying a little bit about what the next chapter is about. It's called reducibility. I won't even, it's a whole new concept. I won't even start on what that means, reducibility, although you can probably guess just from the label. But during that chapter, which is another shortish chapter, about the same length as this one, so chapter 5, we will come across a whole string, a whole bunch of examples of certain languages, certain problems that are undecidable or un-Turing recognizable, and so on. Yeah, a whole bunch of, like, this is our first one. This is the first taste, right? So sort of this opens the door to to a vast industry of people, researchers, trying to find one example after the other of problems that are just unsolvable, uncomputable. There's no Turing algorithm that can compute them in that sense. And a major event of great significance, comparable, debatable, with the significance, say, of Gödel's famous incompleteness theorems. Well, people tend to concentrate on the second one, call it the theorem, but strictly speaking, he came up with 2 incompleteness theorems. Alright, well, I guess I'll stop there. We have passed a major milestone. I hope you appreciate the full gravitas of the situation. Ciao.